So we're continuing working in section 3.4 and kind of piecing together all the things that we've learned about zeros and multiplicities and factored and rational roots and all that good stuff. So number 6 here, they say for this function, find the following. And the degree is, of course, is our biggest exponent, so 3. That's our biggest exponent. The number of zeros will be 3. Whatever that degree is, that's how many zeros you're going to have. Keep in mind, some of them could be imaginary numbers, some of them could be real numbers, but there's going to be 3 zeros. The list of possible rational zeros. That's where we take all the factors of 8, the constant, and we divide by all the factors of 6, our lead coefficient. Now, we've actually done that before. I think it was in video number 1, where we had this exact same function, and we did that already, so I'm not going to repeat all that work, but just know if I take all the factors of 8 and divide each of those separately by all the different factors of 6, I would get this big old list right here, okay? So I'm not going to redo it, but just know that we've done that one previously if you need to consult back to it, okay? So I could rewrite all of those numbers right here. That means if this graph hits the x-axis at a rational number could be a whole number or a fraction, it will be one of these places right here. It will not touch the x-axis at 5 because 5 is not on the list. It will not touch the x-axis at -10 because -10 is not on this list. So that's just something to kind of keep in mind. Okay, now find the zeros and give them multiplicities. Rather than try synthetic division with every one of these numbers until we find one that works, that could take a long time. Rather than do that, let's graph it and let's see if we can kind of get an idea of what the zeros might be. So 6x to the third plus 23x squared plus 26x plus 8. I'm going to graph it. And when we graph it, it looks like it touches the x-axis at -2. It looks like it touches at, I'm not sure what those decimals are, maybe -1/2 and then maybe -4/3. And the reason I'm tempted to think that that number is -4/3 right there is because -4/3 was on our list of possibilities. Okay? So that's why this list can be helpful, is when you go, I can't tell what that decimal is. Is it 1/2? Is it 1/3? It's hard to tell. But if you have a list of possibilities, notice it could have been -1/2 or -1/3. We're not really sure just by looking. But it gives us an idea. Okay? All right, so I'm going to make a note for myself that this graph appears to cross at x equals -2. Looks like that's going to be one that works. Okay? So since it appears that that's one of our zeros, let's try it. And if it works, then we'll, in our synthetic division, we'll get a remainder of 0. All right, so 6, 23, 26, 8. 6 times 2 is -12. 23 and -12 is 11. -2 times 11 is -22. 26 and -22 is +4. -2 times 4 is -8. And that gives a 0. So sure enough, -2 is one of our zeros. Okay? Now, what I'm left with would be 6x squared plus 11x plus 4. Now, looking at my graph here, it looks like it may be -1/2, like maybe -4/3, but I'm not positive. So I could try, synthetic division with -1/2 or -4/3, and I could keep trying until I see if those other numbers work. But since this is a quadratic, I can just use either factoring or quadratic formula, and I can finish this up, okay? So I can try to factor it myself, or if you have trouble with quadratic formula, trouble with factoring, you could do quadratic formula. I'm going to do the quadratic formula, okay? All right, so A would be 6, B is 11, C is 4, and I'll plug those in to my quadratic formula. Alright, so that's going to be x equals -b, so -11, plus or minus the square root of 11 squared minus 4 times 6 times 4, all over 2 times 6. And I'm going to type in my calculator here, 11 squared minus 4 times 6 times 4. And I get a 25 under the square root. And then 2 times 6 is 12. Okay, well, square root of 25 is 5. So negative 11 plus or minus 5 divided by 12. So I'm going to work it once with a plus. Negative 11 plus 5 over 12. And then my other one will be negative 11 minus 5 over 12. Well, negative 11 plus 5 is negative 6. So negative 6 over 12, which is negative 1/2. When I do the negative 11 minus 5, that's negative 16. And negative 16 divided by 12 simplifies to be negative 4/3. So we were right, okay? On the graph here, it is touching at negative 1/2. That's this one right here. And negative 4/3. Negative 4/3 would be negative 1 1/3, which is about where this one is right here. Okay, so our zeros are negative 2, which we could tell by the graph pretty easily, negative 1/2, and negative 4/3. Those are our three zeros. Notice they all have multiplicities of 1. They all got used once. That's why we had three different zeros. Okay, now, what about the last part here? They want us to rewrite this original k of x as a product of linear factors. That means instead of writing it out in general form, we want to write it in factored form. Well, since one of our zeros was negative 2, that means that x plus 2 is a factor. X plus 2 is a factor, then negative 2 is a 0. Okay, now what about the negative half? Well, that's going to be x plus, that's going to be 2x. Let me do that just a little bit here. X plus 2, and another one will be 2x plus 1. Now here's when I know that. If I set 2x plus 1 equal to 0, because remember in factored form you would set each factor to 0, I would minus 1 from both sides and get 2x is negative 1, and divide by 2 to get x equals negative half. So if negative 1/2 was the 0, then positive 2x plus 1 is the factor. So I just kind of picture if I were setting it equal to 0, I would subtract the 1 to get a negative 1 and divide by 2 to get negative half. Okay? By that same logic, if my 0 is negative 4/3, then I bet it was 3x plus 4 as the factored form. Okay? Now, remember a while ago when I chose to use the quadratic formula right here? If I had chosen to factor it instead, I would have factored it to 2x plus 1 and 3x plus 4. If I FOIL this out, I would have gotten back to the 6x squared plus 11x plus 4. So that's another reason when you have quadratic, if you can factor it instead of doing quadratic formula, then you'll get the actual factors to write in your factored form, and that might save you a little time. Okay? So just know this k of x written out long ways and this k of x written out in factored form are the exact same graph. The nice thing about the factored form is you can quickly tell what the zeros are. You can go, oh, that 0 is negative 2. Oh, that 0 will be, subtract the 1 and divide by 2, negative half. That 0 would be, subtract the 4, divide by 3, negative 4/3. And then you can tell real quickly what your zeros are. Okay? Let's try another one here. For this function, find the following. All right, so the degree is 4. That's our exponent, which means there will be 4 zeros. Some of them might be imaginary numbers, but there are going to be 4 zeros. Okay? Possible rational zeros. Well, that means we need to take all the factors of our constant at the end and divide each of them by the coefficients, or the factors of our coefficient. So 4 divided by 1. Well, plus or minus 1, plus or minus 4, because 1 times 4 is 4, plus or minus 2. But on the bottom, all I'm going to have is plus or minus 1, because the only thing that multiplies together to make 1 is 1. So then I take each of the factors of 4 from our constant and divide by our denominator. 1 divided by 1 is 1. 4 divided by 1 is 4. 2 divided by 1 is 2. So if this graph touches the x-axis at a nice, pretty rational number, a fraction or a whole number, it's going to be one of these. There's no way this graph is going to touch the x-axis at 3 or negative 7 or something like that. It's going to have to be one of those. Okay, So let's look at our graph, see if we can figure out what we think the zeros might be. X to the 4th minus 4x to the 3rd plus 5x squared minus 4x plus 4. And when I graph it, if it ever finishes, taking a minute to think about it, looks like the graph hits the x-axis at 2. Positive 2 was on our list. Now, if that looks like it's the only place that it touches, so that's a clue to us that probably some of the zeros are imaginary numbers, and that's why we don't see them touching the x-axis. Now, I also want to point out that it touches at 2, but if you notice, it touches and then it goes back the way it came. That's a pretty good clue that there might be a multiplicity of 2. That x value of 2 got used more than once. Okay? It bounces there, or touches there instead of crossing. So I'm going to make a note that it appears to touch x equals 2. And I'm going to write multiplicity of 2. And I'm going to put a little question mark on that because I'm not positive. I have to try it. But because it touches instead of crossing, I think it might happen more than one time there. Okay? All right. So let's check it. How do we check and make sure that it works? We plug a 2 in the box, and we do our synthetic division. So write out my coefficients. 2 times 1 is 2. Negative 4 and 2 is negative 2. 2 times negative 2 is negative 4. 5 and negative 4 is 1. 2 times 1 is 2. Negative 4 and 2 is negative 2. 2 times negative 2 is negative 4. Sure enough, we get a remainder of 0, so that worked. Now, because I thought that might be a double root, because I thought the multiplicity might be 2 there, I'm going to try 2 again. Okay. Also, my original exponent was 4. This depressed polynomial is a 3. I can't do quadratic formula on it if the exponent is a 3. So I'm going to try one more time. I need to get it down to a quadratic. Okay, so I'm going to try the 2 again. 2 times 1 is 2. Negative 2 and 2 is 0. 2 times 0 is 0. 1 and 0 is 1. 2 times 1 is 2. Sure enough, that works. Okay. Now this depressed polynomial right here is x squared plus 1. So x squared plus 0x plus 1. I'm going to set that equal to 0, and I'm going to solve this. Now, because it's missing the b part here, I could just do square roots. So I can subtract 1 on both sides. X squared is negative 1. Take the square root. Square root of negative 1 is I, or negative I. And I kind of expected some imaginary numbers there because I was only seeing the graph touch the x-axis in one spot. Double root, because it got used twice, because it was touching and then going back the way it came. But that's only 2 of my zeros, and I needed 4. So it sort of makes sense that the last 2 would be imaginary. So our zeros are 2 with the multiplicity of 2. Got used twice. I and negative I, and each of those had a multiplicity of 1. Okay, which means rewriting this as a product of linear factors. So m of x equals x minus 2. Okay, if 2 was the 0, then x minus 2 is the factor. That got used twice because it had a multiplicity of 2. Another 0 was I, so I'm going to say x minus I. And the last one was negative I. Opposite of negative I is positive I. So x plus I would be my last one. This is the factored form of this original polynomial function. If I were to graph this right here, if I type this in my calculator, I would get this exact same picture that we got right here. Okay, let's try another one. Let's see here, number 8. So the degree, well, our biggest exponent is 4. That means there's going to be 4 zeros. Some might be real, some might be imaginary. List the possible zeros. We've actually, I think, already done, no, did we do that one? We're going to skip that if that's okay, just because, you know, we can find all the factors of 65 divided by 1 and 2. I'm going to skip that if that's okay. And I'm just going to go straight to finding the zeros. Okay? So finding the zeros, we're going to graph it. And we're going to look and see where it looks like it crosses the x-axis. So 2x to the 4th plus x to the 3rd minus 35x squared minus 113x plus 65. Make sure I typed everything right. And it looks like this graph touches at 5. That one's pretty obvious. And this one, it's kind of hard to tell, maybe 1/2. And if you think about it, 5 would have been on our list. Make a note here. Appears to cross at x equals 5 and x equals 1/2. 5 would have been on our list of possibilities because 5 is a factor of 65. And 1/2 would have been on our list because 1's a factor of 65 and 2 is a factor of 2. So positive 5 and positive 1/2 would have been on our list if we had finished making this list of possibles. So I'm pretty confident in those. I'm going to try my synthetic division with those. I'm going to put a 5 in the box, write out my coefficients. Five times 2 is 10, 11. 5 times 11 is 55. Negative 35 and 55 is 20. 5 times 20 is 100. Negative 113 and 100 is negative 13. 5 times negative 13 is negative 65. That does give a remainder of 0. So 5 works. I'm going to try 1/2. Try the 1/2. Bring down the 2. 1/2 times 2 is 1. 11 and 1 is 12. 1/2 times 12 is 6. 20 and 6 is 26. 1/2 times 26 is 13. That also gives a remainder of 0. So those, the 5 and the 1/2 definitely did work. Okay. My depressed polynomial. Notice I started with an exponent of 4. So the first synthetic division I did knocked it down to an exponent of 3. The next synthetic division I did knocked it down to an exponent of 2. So 2x squared plus 12x plus 26 is my depressed polynomial. That's a quadratic. It's an x squared. So I can solve to get my last two zeros. I can try factoring. Factoring's not going to work. I'll just let you know. Or I can try quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. Remember the a is going to be 2. That's in front of the x squared. The b will be 12. And the c will be 26. I'm going to plug those into my quadratic formula. So negative b is going to be negative 12 plus or minus the square root of 12 squared minus 4 times 2 times 26 all over 2 times 2. When I plug that into my quadratic formula, 12 squared minus 4 times 2 times 26, I get negative 64. Notice that's a negative number under the radical. When we have a negative number under a radical, we get imaginary answers, don't we? 2 times 2 is 4. All right, so square root of negative 64. Well, that's going to be 8. 8 times 8 is 64, but I got to put an I on it because it's imaginary. You can't take the square root of a negative. Divide by 4. So notice the negative 12 gets divided by 4, and the 8i gets divided by 4. Negative 12 divided by 4 is negative 3, and 8i divided by 4 is 2i. So negative 3 plus or minus 2i. Okay, so what are our zeros? Well, 5 was one of our zeros. We tried synthetic division and it worked. Got a remainder of 0. 1/2 is one of our zeros. We tried it and it got a remainder of 0 in our synthetic division. The next one is negative 3 plus 2i. And the last one is negative 3 minus 2i. Those are the 4 zeros. Okay? So in factored form, they want us to write wx as linear factors. Write it out in factored form is what they're saying. So since positive 5 was a 0, x minus 5 is going to be a factor. since 1/2 was a 0, do you remember how to do that? 2x minus 1 is going to be a factor. Remember, whatever's on the bottom would be in front of your x, and then whatever's on top would be the constant by itself. We've got to use the opposite sign. Okay, now, -3 plus 2i is a 0. So I've got to put x minus whatever this 0 is, just like we did x minus 5 or x minus the other one, okay? When I subtract these, that 3 will become positive, and the 2i will be negative. So x minus 3, I'm sorry, it's going to be a plus right there. Because if I did x minus -3 plus 2i, it's normally what we would have, and I distribute that negative, I would have x plus 3 minus 2i, okay? And then the other one, x minus -3 minus 2i, when I distribute that -3, I'd have plus 3 plus 2i, okay? So my other 0 would be x plus 3 plus 2i, and there's our factored form right there, okay? All right, sorry that video was a little bit longer, but I think we got some good examples in there.